Okay, today we're going to be discussing force and tension. We're going to be using our same equations that we've had for quite some time. Specifically, we're going to be working a lot with friction here. N is m times g. The normal is mass times gravity. This has to be something that you know without having to think about. The normal is mass times gravity. Today, we're going to review how to draw free body diagrams. We're going to identify the forces acting on an object. Then we're going to show those with the free body diagram. We're going to calculate the normal, the weight, and the static frictional forces. Newton's first law. Newton's first law deals with when an object is moving, it's going to stay moving. When it's at rest, it's going to stay at rest. So as we said here, so when we had our marble drop, what was happening here is the marbles were rolling down the hill, and Newton's first law says an object in motion tends to stay in motion, so its horizontal velocity was going to stay the same. Even though it was acting in a projectile motion, its horizontal velocity stayed the same, and that was because of its inertia. Newton's second law. Newton's second law is where we start coming up with all of our equations that helped us calculate force. But it basically says that if we put some force and apply it to an object, whether it's a cat, a dog, a car, a spaceship, if you apply a force to some object and that object has mass, it's going to cause that mass to accelerate. There's no way around that. So if we let's just simply take a car. There's our car. Put some wheels on it. Probably should have made it vice versa. At any rate, if we apply a force to that car, it's going to cause it to accelerate forward. Right? It's going to accelerate. Newton's third law says when a force is exerted on an object, that object exerts an equal and opposite force back. So, let's draw a wall right here. Alright, we've got a wall. And let's draw a person. So we've got this dude right here. He's getting ready. He's here. There's his legs. He's pushing. And he's got his hands up here on the wall. And he's got his head here. So let's give him a head. What's going to happen? He's going to take his head and he's going to bang it into the wall. Well, when he does that, the wall is going to exert an equal and opposite force back on his head. So if he hits the wall with 100 newtons, the wall is going to hit him back with 100 newtons. That's just the way it is. There's no way around that, and there's no way to change that. Alright, here's what we want to talk about today. Inclined plane and force problems. Well, what we've got here is I want you to understand that whenever something's acting on an incline, there's a triangle that's formed, and it's these three things. The normal is going to act at a right angle, so we've got the normal drawn in here, depending on what the angle is. The other part of the triangle is the hypotenuse, and that is the object's weight. Right. Notice that this is going to be the longest component in this triangle. All right, so that's why it's the hypotenuse. The last component that we want to talk about here is the opposite side. And the opposite side, depending on how the triangle, how much the incline is, the opposite side dictates how much force there is pushing or pulling an object down the hill. On a small incline, there's only a very small amount of force pushing something down the hill. So, for example, a sled may not slide down this hill because it's not a lot of force. But this is why it's a lot of fun to go sledding down a big hill or a steep hill, because there's a lot of force, and you'll start traveling. That force applied to the sled is going to cause that sled to accelerate, because if you can tell by the length of the vector, this force is very long. Well, we're going to use this in our frictional problems. This opposite, what we find out is if the object's not moving, then the force of friction has to be equal and opposite. So in this case, my frictional vector here is not the same length as my opposite. So this object is not in equilibrium. So what do you think this object's going to do? It's going to slide down the hill. In this case, my force of friction, which I'm trying to make be equal and opposite, in this case, the force pulling it down the hill and the frictional force, which is opposing it to move, are equal and opposite. So we would say that this is an equilibrium. So it's under static frictional. The friction is static friction. Well, let's look at a problem here. All right. It says find the normal. Well, in this case, the normal is the adjacent, and there's really not anything I can do with that just as of yet. The next one says to find the weight. This one is one that I can do right away. I can find the weight. That's simply by taking mass times gravity. The weight in this case then is 2,940 joules, and we did that by simply taking 300 times 9.8, and it probably should be a negative. It's negative 9.8. The next thing here then is it tells me to find, I can now go back up and find the normal because my triangle is starting to be filled in. I know the hypotenuse, I know the adjacent, or I'm going to find the adjacent now that I know the hypotenuse. The other thing that's important is if this is a 20-degree angle, then that's what this is. It's a 20-degree angle up here. Well, which trig ratio uses adjacent and hypotenuse? Well, that's cosine. So I can simply say then that this becomes mg cosine of 20 degrees. That turns out to be 2,763 newtons. And yes, I rounded there a little bit. So that is my normal force. That's how much force is pulling up on it. Find the frictional force. Well, it tells me that this object is not moving. It's not moving. So I know that the frictional force acting on this object is heading in the opposite direction. And the force pulling it down, the friction and the force pulling it down, they have to be equal and opposite, even though I haven't drawn the arrows the same here. So if I find out how much force is pulling it down the hill, because I know it's not moving, I know that the frictional force has to be equal to that in this case. So find the frictional force. Well, the frictional force in this case is going to be equal and opposite to mg sine of 20 degrees. It's mg sine of 20 because if you remember back to our previous slide, right here, the opposite side, the one that's being pulled down, is mg sine of x, or mg sine of theta. So that's what I did here. I took 2,940 times the sine of 20, and I got 1,006 newtons, and I rounded there a little bit. So that gives us, and that tells us how to find this frictional force. Now, how much tension is in the rope? What is the mass of the hanging box? We're not quite ready for that. We're going to cover that some in class tomorrow. What I want you to do is I want you to take chance here, take some time, and forget about these bottom two here. I want you to find these first three. If you can find these first three, and I'm going to give you a hint, all right? That's mg, as we said on 2 slides ago. This right here is going to be mg cosine of x, and this is going to be mg sine of x. If you can come into class tomorrow knowing those 3 things, you're going to be way ahead of the curve. Hey, I've really enjoyed this lesson. I'll see you on the flip side.